So welcome to the session on the introduction to advanced DSP and the applications. Today, what we're going to discuss today we're going to discuss about the overview of DSP and applications, the big picture of the DSP. So introduction to advanced DSP and why to use DSP. What do you mean by advanced DSP? We'll just do with a case study there, and what all the measurements are required for DSP, and what is the current research going on in DSP. So the state of art technologies using DSP, and finally, what is the career path for DSP engineers? That how do you grow as a DSP engineer, and what all the field of work you'll be working when you mature as a DSP engineer. And we'll talk about the job opportunities and how do we bridge the gap for the expertise, what the industry needs, and what you have learned in academics, right? So we'll talk about this. So we'll get started with the overview of DSP there. So I think everybody would have studied DSP in the academics. So DSP, it takes the real world signals, digitized signals, which are sampled, quantized, and stored in the memory. Okay, the DSP. We know the basics of DSP is that it is something like you take a digital signal and you want to process the signal and you want to show some result to the signal based on the content of the signal, right? So that is what the DSP means. So it takes the real world signals, so which are sampled. Which the sampling rate could be different for each of the different criteria, right? And quantized. So quantized means that I think everybody knows about the quantization and how the digital quantization works. Because I think we don't need introduction when we have good amount of knowledge in the communication systems. Okay, and basically the signals are stored in the memory. Means that what all the signals what you get, right? They're all present in some data memory, right? So and then we have to access this memory and we have to do some processing on it. Okay. So examples of some of the examples that when we talk about DSP is that, for example, of a DSP signal could be is that an audio signal, a video signal, a sensor data, and data transmitted from the source like satellites, mobile station, optical fibers, optical cables, Wi-Fi, Bluetooth, etc. They're all dependent upon the DSP, right? Because they're all coming on in the form of a digital and form of an analog signal, which are quantized and stored in the memory. Okay, so this is the overview of the DSP there. So then and then once we store in memory, what it is going to do there? So DSP is something like it does most of the mathematical operations on these signals. For example, it could do an addition, subtraction, multiplication, division, okay, within a limited amount of time. So with you can use some specialized techniques. Like for example, one technique could be is that you might need to do something like multiple operations when compared to the conventional processor. For example, if you take an ARM9 controller or an ARM controller, right? It can do only one or two operations at a time. But with DSP, we can generate a lot of instructions and we can do parallelism in detail that one. So that we'll study in the next slides there. Okay. And second thing, how do we compare with respect to the general RISC and the CISC processor? For example, if I take the Intel processor and if you take an ARM controller, so how do we differentiate that? How DSP means that what are the specialized techniques available in DSP when compared to RISC and CISC? Basically, is that one basic requirement is that DSP operates in a constant environment, and it matches the real-time performance. Okay, because one thing is that when you have the real-time performance, right, it means that you are bound to a timeline that you have to complete within so and so time. If you're not meeting the time, then it means that you're going to lose the sync, or you're going to lose the data. Because as I said, that one, you're going to store the DSP something like you store all the data in the memory and you have to complete all the operations within limited time. Okay. So this is the first definition of DSP there. Okay, we'll just talk about the big picture of DSP. So how DSP is used in the real world. As I said, that one that we get signals in different domains, right? For example, it could be in the video domain, audio, or wireless domain. So once we get the analog signal, then what we do is that the signal receiver will just store all this analog data there, and the signal is digitized. Means that you are using an A to D converter and something like quantization there, and then you just deploy a filter there. So why do we need a filter in the very first stages? Because we know that the signal is added with some noise components, right? So basically, we want to filter out some of the components that we don't want to take it up, right? So what the first thing the DSP can do is that once you have the digital signal, it can filter out some of the out of the band noise signals. Okay, this is done by a digital signal processor. Okay. So what does the digital signal processor, how exactly is it different from the conventional processor? Okay, I'll just give a brief overview of that one. So basically, when you take the normal architecture, okay, when you take the normal CISC or the RISC architecture, basically we have a program memory and a data memory, okay, and which are multiplexed and which could be in two different locations also, right? But in case of DSP, we have two separate access to the program memory and data memory. It means that you have limited amount of program memory that can be up to around 1 MB or 2 MB data, and data memory can extend up to 64 MB data. In for just an example there. So what this will do is that this is going to speed up your operations. Means that because it has a constant memory and it is accessible, addressable, right? You don't need to fetch the data from anything like RAM, right? So you have everything in the program memory, which is something like within the controller itself. So with this one, it's going to accelerate your conversion there, all the computations. Okay. So this is one example of the digital filter that just given that one. So that I want to filter out some of the noise, some of the noise which is not present in the in band, basically present in the out band there. So and then next, what I will do that I'll just pass on this filter data to a controller. It can be something like a general controller like ARM or Intel controller there. So based upon what is the requirement there. Okay. So next, when the controller will the controller can do every task what is supposed to be done, because if you take an example of a tablet or a mobile application, right? So for example, somebody is sending a video. So what all the information what you need for that video there? So first thing is that we have to have a display for the one, and then we have to have this audio. Means that audio also is required for the one. And along with that one, we have some sensors, right, fitted for a mobile phone. For example, based upon your light intensity, everything, the display, the intensity changes, the display intensity or the brightness and the contrast can change. So this is done by signal conditioner, means that it's coming through a sensors there. So this DSP, what will do is that it is going to have a separate program memory and a data memory, and then it is going to demux. It means that you have to demultiplex your audio and the video signals. So basically, the video is something like if you take an MP4 file, it has got both audio and video. So you have to extract some part of the audio and some part of the video, and then they have to be displayed on the video is displayed on your display there on your LCD or LED display, and audio has to go to the speakers, right? So it means that both of them has to be in sync with each other. So for example, some cases you can see that the video comes first and audio comes slower there. So in that case, we lose the synchronization mechanism sometimes. So all this controller has to be done by a DSP there. So DSP is just not only for filtering and other applications, but it has got a diversified applications starting from your basic encoding, decoding, and demuxing, and also up to the display buffering part also, some part of display buffer part also, that I will explain in the details in the next slides. Okay. So as I was just discussing that I mentioned this as optional, the filter may not be required all the time. So means that instead of filtering it before you pass it on to the controller. For example, the controller can be something like turn on your video, audio, or put in mute. This is going to take some other actions. So this can be the entire filtering can be done in this stage also, in this DSP stage also. So that we'll discuss how it can be done. Okay. So we'll just study about the basics of DSP there. So now let us go. What is more advanced in DSP course? Okay. So we'll just talk about what is DSP, where DSP is used, and how DSP is relevant to engineers and when to use DSP. So basically, we just discussed about DSP, that it's going to store a digital signal in your memory there. Okay. So where is DSP used? So if you go back to the previous slide, it's used in multiple places. That it can be your audio signal, your display signal, and a signal conditioner, means that's a sensor data, and also you're getting the data from the real world, right? For example, you're doing some filtering, right? Filtering and channel estimation, everything, right? So that's part of the wireless communication also there. Okay. So DSP is used in most of the domains which are responsible for maintaining the real-time performance. Okay. So how is DSP relevant to engineers? So just assume that if you do not have DSP in a DSP system, a DSP processor in your mobile, or if you have a generic controller there, so can we meet the timelines of what is required for the real time? It's very difficult because we have to emulate multiple amount of parallelism within that controller. and it's going to increase the cost of the on device there. For example, one such example could be is that if you're not using DSP for an audio, right, and if you're using a generic controller, okay, so what can happen is that you can get the same quality, but at a higher computational rate. That one means that you have to increase your computational rate because a double or something. That one, so that's going to take a toll on your battery performance there. Okay, and one more thing can be is that, for example, if you are trying to implement a wireless an algorithm, ARM or a Intel platform, so that can be a very expensive solution because the timeline for maintaining the buffering control, right? For example, in wireless, right, all the data is in real time, and you have to store the data, and you have to process the data within some timeline. If you're not able to process the data within the timeline, it means that you're losing the data and you're not able to process for the next one second. So it means that it's a signal loss situation there. So these are the situations when we have to use DSP to emulate the speed, and also with respect to avoid the taking extra memory and limited resources there. Okay. So DSP for engineers and scientists. So how is advanced DSP course different from what we study in academics? So, okay, during the academics, right, we study up to the digital filter part, and also to some extent on the Fourier transform, the Fourier, what is it on the Fourier transform, the FFT algorithms, and some part on the speech signal there. But is it sufficient for you to be a DSP engineer? But that's where we have to think about the different angles of one. For example, one thing is that, okay, I made a FFT, but when can I use the FFT, and how efficiently can I implement this FFT on a particular controller to make it more different from what I am expecting that one. Okay, this is when we need some case studies, and we have to implement some of the modules and some of the things that what has to be applied on with respect to making it a real-time performance. Okay, okay, let's just go to what is real-time. Real-time that one. So real-time means that it's not like zero delay or something that one. Okay, it's nothing but there's nothing computation which can happen in a 0-second time that one. For example, I get the data on a wireless signal that one. Okay, and then I have to complete the processing of that wireless signal within the 2-millisecond window. I have a 2-millisecond window, and I'm just going to take 2 milliseconds to compute what is present in the wireless signal, and I have to decode the data and give it to the next layer. For example, it could be a MAC layer, or it could be the next higher layers there. Okay, so what exactly real time means that, so if we get a frame at time is equal to t is equal to 0, that's called as air time. Okay, and we have to complete the processing of the full data within the air time of t plus 2, that is after 2 millisecond interval. And then this 2-millisecond interval, whatever we are getting, whatever we are storing the data, it is going to recompute the time, saying that, okay, it is a t is equal to 0 to the next MAC layer, so that we don't lose the synchronization with respect to the timeline that one. So this is when if we can predict that, we can compute the timeline, we can compute the processing within this particular timeline, then we can achieve the real-time performance. Okay, that's something like a window mechanism there. Okay, so the 2-millisecond is something that we have to keep the timeline to make sure that we can deliver what is required for the higher layer there. Okay, this is called real time. Okay, now next thing, what comes into mind? So we studied about the DSP and digital filters, and we implement digital filters using the floating point unit. So can we use the floating point unit in DSP all the time, or is it going to take a toll on the performance and also on the cost? Yes, that is one very good, interesting question that we have to find an answer for that every time. Okay, so floating point is that, okay, you know that the floating point works well, and then it actually gives the precision. But can floating point be used in every scenarios? The thing is that it is not going to be used every time, that one, because it is going to take a toll on the performance, the first thing. And second thing is that even if you're using any accelerators, anything, that you have to convert the data to fixed point, because the fixed point is always recommended for DSP because of the speed and with respect to the cost also there. Okay, so we have to implement most of the 99% of the DSP algorithms are implemented in fixed point, except for few cases that where we have to use some floating point, and that's only for the case of the military purpose and also in satellite communication. Okay, And what are the complexities in implementing on a DSPs? For example, I made an algorithm that an algorithm will take the data from the source. It will find out what is the how much of noise variants are present in the signal, and it will give the report that okay, this is so much of SNR has to be SNR is there. So how can we implement this entire algorithm on the DSP? As I said, that one that floating point is very simple, but we have to implement all of these things in a fixed point DSP. And there are some complexities that we have to follow. For example, we have to not lose the precision, and we have to make sure that the DSP, whatever we are implementing, right, should be in a human readable format. For example, if we can implement some algorithm, and if the output is not readable, right, by any human readable format or any format which the MAC layer expect, right, what is the point in implementing that algorithm? Okay, so this is when I think that we need to implement the algorithms such that it has to be time bounded, and also the data has to be bounded so that it is not going to lose the precision as well. Okay. Next thing is microcontroller like ARM and Intel compared to DSP. Can we compare that microcontrollers? It's not comparable. The reason is that the first thing is that the DSP emulates some of the mathematical operations when compared to the conventional ARM and Intel. The reason is that Intel is basically a CISC controller. Okay, so Intel is basically for Windows application and Linux applications, and mostly for server applications. So if we use the same Intel to compute a DSP algorithm, that's going to take a huge amount of toll because it's going to use a CISC architecture, and it's not going to exploit the parallelism when compared to the DSP. Okay, how about ARM in this case? So, for example, if we have a 4-core ARM or an 8-core ARM, can we compare to DSP? Yes, we can compare to DSP, but the thing is that some of the things in whatever we get the parallelism with respect to ARM, right? That cannot whatever parallelism what we get in ARM is lower, is much less what we get in DSP side. Because if you take a 4-core DSP and an 8-core ARM controller, the DSP performs much higher when compared to the ARM controller. Okay. The reason is that the ARM controllers are time bounded and limited to some extent because of their architecture level. But whereas in DSP, there is a flexibility that we can achieve parallelism in 3 stages. One is with respect to the algorithm level of the parallelism. One is with respect to the module level parallelism, and third thing is with respect to the instruction level parallelism. Okay. Okay. Now I can use a DSP, but how can I code in DSP? Okay, if you want to code in DSP, what you can do is that there are some various amount of tools and available. And also, if you want to develop an DSP algorithm, if you want to implement DSP algorithms, you have to be specific to some DSP platform. It can be a TI platform or an KVM platform. Okay, so you can code in multiple platforms. Okay, which programming language can be used to build the DSP system? So you can use either C or C++, or if you are good in assembly, you can also use it for DSP. So now we'll just do a case study for the DSP. Okay. So I think most of you know about the H.265 standard, that one, ISO IEC H.265 standard. It's basically a video standard for encoding the raw video into a compressed video and help in streaming on the data on the network there. Okay, the first thing. So second thing is that you can also think about the bit rate processor for the 6678 chip, the Texas Instrument 6678 chip. Okay, this is actually for the wireless platform. Okay, let me just go through the case studies in the next slides there. Okay. Okay, so what makes DSP different from CISC and RISC architecture? So in the previous one, I'm just talking about the CISC architecture, that you can implement an algorithm in the Intel platform on your Intel x86 or the i7 core also. But what exactly the difference is that I told you, right? That's one thing is that with respect to the parallelism, the first thing is parallelism, because we need to have an instruction level parallelism, which makes the DSP much more efficient, something like 4 times the higher speed than the Intel processor. The first thing. Second thing is that when using a DSP architecture, the memory is limited to something like 1 MB or 256 KB in some cases. And this memory is within the same chip there, within the same one core there. So now, if you know with this approach, right, what it's going to speed up is that it's going to speed up your memory access every time there. Okay, that's the first thing. And third thing is that the DSP has some different modes of DMA, which can accelerate your data movement across the cores there. For example, if you want to move some data from a sys core or a RISC core to one core to other core, means that you have to use a shared memory concept. Whereas in case of DSP, we have some different types of DMAs which we can emulate without using much of the shared memory. And this makes the DSP much more at speed, computational speed with respect to the CISC architecture. Okay. So we'll just talk about the next slides, that's career path in DSP and opportunities in the next slides. Okay. So, okay. So why do we use the DSP? The first thing, we'll go back to the basics of the DSP there. What is sampling? That one? Sampling is process of converting the continuous time signal into discrete time signals and quantization, as I said that one. So why do we follow the Nyquist rate? Because to reduce the aliasing effect of the Nyquist rate. Okay. So if you are sampling at a higher rate, for example, to maintain the quality, then is it going to take a toll on the performance? Yes, maybe yes or no. Maybe it could be, because it depends upon the type of application where you're looking at. For example, at the speed signal, right, you may not need to oversample at higher speeds. Whereas in case of wireless, you may need to sample at higher rate because to reduce the effects of the channel impairments and noise signals. Okay. So what is noise? Noise is basically that it's an infinite bandwidth signal, and it distorts and it reduces the probability of detection of signals. For example, when we talk about noise, right, in DSP, so noise has a very infinite bandwidth, and it's something like it's not correlated at all. There is no correlation between one point to other point in noise there. Okay. And second thing is that what noise can do, noise can distort a signal, it can attenuate, or it can also add up your signals with some harmonics there. And if there is a more amount of noise in the signal, the signal detection can fail, right? For example, in DSP, we talk about a term like signal to noise ratio, right? SNR ratio. And we talk about different terms called as the RSSI. There are some terms called the RSSI, that's called as the reference signal strength indicator signals. So these all detect that how well the signal can be detected in the presence of noise and in presence of the channel impairments. So, okay, channel impairments. What does channel impairments mean? Channel impairments means that if you pass a signal through a channel there, it is going to undergo some fading effect. Okay, the fading can be across the full bandwidth of the signal, or it can be some part of the bandwidth of the signal. So it can basically it can attenuate the signal, and it can also change the phase of the signal. Okay, resulting in harmonics of this. Okay, so what are the fundamental operations that DSP can perform? The basic fundamental operations is that we all of us know that one is the addition, subtraction, multiplication, division, and it's something like we have something called as a gain factor, and we have some delay elements. Okay, these are the basic operations of DSP system. Why do we need the delay elements? That I think I'll just cover in the next slide when we are going to the filter there. Okay, so can we implement all of these operations in programming languages like C, C++? Or something there? Yes, we can implement in C, C++, Python also to some extent, and MATLAB is basically for simulation, not for implementation there. Okay, so it's actually very easy for DSP engineers to groom in C, C++ or MATLAB, but Python it will take some time because the libraries are not fully available, and some libraries are commercial ones. So means that we have to procure a license and use the libraries there. So what all the challenges are faced by DSP engineers to implement these of the mathematical operations there? So as I was talking that one, first thing is that with respect to the speed and space, and third thing will be the challenging is that how do you exactly map the algorithm on the real-time target? For example, if you're taking a TI-6678 platform for the wireless bit controller, so can we map the entire algorithm without using any libraries, but using some of the instructions itself, so that because if you use a library, the library is not, the timeline of the library may not be predictable sometimes. So it may take higher time than what is expected. So these things have to be make sure that we have to use some sort of instruction level parallelism so that we can get the best out of the DSP, whatever with the processor, what are the controller, what we're using there. So that's basically with respect to the speed operation and also the maintaining the quality of data. That's the most important thing. That, for example, when we're using since we're using a fixed point operation, there is some loss of precision, but we have to compensate for the quality. If we're not maintaining the quality, there's some level of distortion in your final signal, and it may not be up to the mark. Okay, so these are the challenges faced by the DSP engineers. Okay, now I just talked about the delay element in the filter there. So can we just think that one? Just think about an IR filter. Okay. So can we implement? Can we know that we know how to design that the filter in using the MATLAB or using some of the tools what we know what we study in academics? Can we implement the same filter in the time domain? So yes, the reason is that we can implement this using a sample C++ code there. Okay. So basically, if you take that IR filter form, the form one filter, right? So these REG elements are nothing but your delay elements. That's basically the Z inverse elements there. Okay. And then these are the coefficients. The B0, B1, and the Bn are the coefficients. Okay. And A0 to A1 are the coefficients for your the other one, the feedback one there. So using this one, we can implement this filter. So how can we implement this filter in the time domain in the C++ code? Oh, sorry. So I'll just talk about the IR implementation in the last slide. Okay, once we complete this session there. Okay, I'll just share the code to you, sample code, how to implement the IR filter. So DSP applications field. So where exactly we use the DSP applications? So one thing is that I was just talking about in the wireless communication side, we use the DSP extensively. We use the DSP 99.99% we use DSP there. Okay, video and image processing we use the DSP side. Because video, sometimes we can use something like some third parties, GPUs and other things to emulate the signal there. But to some extent, it's all based on the DSP architecture itself there. Okay, DSP in video and image processing, and also in the audio processing. So video includes audio also. Okay. Next thing is that in military applications and space technologies, this is very important that the DSP is not just about the commercial usage of that one, but military applications have very, very big role when compared to the other applications, and it's actually very, very critical for to use DSP, and most of the engineers are working in this military application and space technology. So DSP, where we exactly use DSP in wireless communications. Okay, so we use DSP to emulate the real-time performance. I'm just talking about the first thing, that we have to maintain the target and we have to make sure that we can meet the real-time performance. And then next thing is that we use in most of the advanced technologies like 4G, 5G, the Wi-Fi, Bluetooth, etc., the wireless communication side. These all use DSP because the reason is that maintaining this performance level, what we have with respect to the other application side, it's quite difficult, and we need to use this DSP to emulate this. Okay, and DSP plays a very important role in the physical layer and to some extent in the MAC layer, because if you take the what is it on the first model, the OSI model, we have the physical layer. Okay, on top of that, we have the MAC layer. So for physical layer detection, right, for signal detection and signal processing, right, we have to use a DSP for any technology. It can be for optical fiber, for 4G, 5G, anything, and Wi-Fi, anything, right? They are all different, right? Each of the technologies, right? So we have to use the DSP for very much in this details. Okay. So DSP is also used in L1. That's called as the physical layer. Okay, L1. I mean, it's not Li. It's actually L1. It's also called as the physical layer. And it's important for real-time performance. I was just talking about the one example that once we get the wireless data, right, we have to complete the decoding of the wireless data within 2 milliseconds and send this data to the MAC layer. That's where we need to have a constrained performance for this. Okay, so in the physical layer, and how DSP is used in the physical layer. For example, if you think any communication receiver chain. So we have something called as the FEC encoding. That's called power error correction coding. So mainly it can be a conversion coding or a turbo coding there, or it can be LDPC as well. Okay, these are because this is actually to prevent the loss of data. For example, when the signal attenuates or changes the phase, right? So we need to have something like a redundant version of the bits so that we can try to extract the information from this. Okay, this is when we use FEC coding there.